Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin our journey through the cosmic emptiness that surrounds us, take a moment to get comfortable wherever you are. Where in the world are you watching from? A quiet bedroom where the day has finally released its grip? A cozy corner where you can finally let your thoughts settle and drift? Tonight we're going to explore something remarkable and slightly unsettling, though I promise you'll sleep peacefully by the end. We live in what astronomers call a cosmic void, an enormous bubble of nearly empty space stretching hundreds of millions of light years across. We'll discover what voids actually are, why they exist, what it means that we're inside one, and whether this affects our understanding of the universe itself. It's a journey that spans the largest structures in existence and asks questions about our cosmic address that scientists are only beginning to answer. But don't worry, this isn't going to be an alarming revelation about cosmic danger or existential dread. Instead, we'll move slowly and carefully through the science of cosmic structure, the discovery of voids, what makes them empty, and what it tells us about where we are in space and time. By the end, I think you'll find there's something deeply peaceful about understanding our place in this vast cosmic architecture, even if that place is more isolated than we once thought. If you enjoy these calm explorations of cosmic mysteries, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being here, for coming back to these slow drifts through space and time. So settle in now. Let your shoulders drop away from your ears. Take a slow breath, deeper than the last few you've taken today. And let's begin our slow drift through the cosmic void that is, improbably, our home. There's nowhere you need to be right now, nothing you need to do. Just listen, and let the story of our empty cosmic ocean unfold around you. Let's begin with where we are right now, in the largest sense possible. When you think about Earth's cosmic address, you might picture our planet orbiting the Sun residing in the Milky Way galaxy, and the Milky Way as part of a cluster of galaxies. That's all true, of course. But there's another layer to our address, one that astronomers only understood relatively recently. We live on the edge of something called the local void, and that void is far larger than anything in our immediate cosmic neighbourhood. The local void stretches roughly 150 million light-years across. To give that scale some meaning, consider that our entire local group of galaxies, including the Milky Way, Andromeda, and dozens of smaller galaxies, could fit inside this void many times over. The void is not completely empty, but it contains far fewer galaxies than the region surrounding it. Where you might expect to find thousands of galaxies, you find only a handful. It's as though someone scooped out a massive bubble from the cosmic distribution of matter, leaving behind a region of profound emptiness. We discovered we lived near this void in the 1980s, when astronomers began mapping the three-dimensional structure of the universe with new techniques. Before then, we knew galaxies weren't distributed randomly, but we hadn't grasped just how empty some regions were. The local void revealed itself gradually. As survey after survey showed fewer and fewer galaxies in a particular direction. Scientists realised they weren't looking at a gap in their data, but at a real absence of galaxies stretching across a significant fraction of the observable universe. What makes our relationship to the local void particularly interesting is that we're not inside it, but rather on its edge. The Milky Way sits on the boundary between this vast emptiness and a denser region of space. This position has consequences for how we observe the universe, for the motions of our galaxy, and possibly for the conditions that allowed us to exist in the first place. Standing on the shore of this cosmic ocean of emptiness, we're able to look both into the void and away from it, seeing the universe from a perspective that might be relatively unusual. The void pulls on us in a sense, or more accurately, the denser regions around the void pull more strongly, creating flows of galaxies that move away from empty spaces and toward regions of greater density. Our local group is moving through space at hundreds of kilometers per second, drawn by the gravitational influence of distant superclusters and repelled, in effect, by the emptiness of the void. We're caught in currents shaped by the largest structures in existence, flowing through the universe along paths determined by cosmic architecture we're only beginning to fully map. And this brings us to something equally remarkable. The local void is not unique. It's just one void among thousands that we've identified throughout the observable universe, each one a bubble of relative emptiness in the cosmic web of matter. Understanding what voids are, why they exist, and what they tell us about the universe requires that we zoom out from our local neighbourhood and consider the structure of space itself on the very largest scales. Picture the universe not as a random scattering of galaxies, but as a vast three-dimensional web. Along the strands of this web, galaxies cluster together in long filaments and dense nodes. Between the strands stretch enormous voids, bubbles of near emptiness that can span hundreds of millions of light years. This is the cosmic web, the largest known structure in the universe, and it shapes everything about how matter is distributed across space. The cosmic web emerges from the initial conditions of the universe itself. In the moments after the Big Bang, matter was distributed almost uniformly, with only tiny variations in density from place to place. These variations were minuscule, differences of perhaps 1 part in 100,000. But gravity is patient and relentless. Over billions of years, slightly denser regions attracted more matter, growing denser still, while slightly less dense regions lost matter to their denser neighbours, becoming increasingly empty. This process of gravitational amplification transformed subtle ripples in the early universe into the dramatic structures we see today. The first comprehensive map of this cosmic web came from surveys in the 1980s and 90s, when astronomers measured the positions and distances of hundreds of thousands of galaxies. When they plotted these galaxies in three-dimensional space, a stunning pattern emerged. Galaxies traced out sheets and filaments surrounding vast empty regions. The structure looked remarkably like soap bubbles, with galaxies concentrated on the surfaces where bubbles meet, and vast emptiness filling the interior of each bubble. The universe, it turned out, was not a random distribution of matter, but a highly organised foam of structure. The filaments of the cosmic web are where most galaxies live. These rivers of matter can stretch for hundreds of millions of light years, containing thousands of galaxies flowing along gravitational currents. Where filaments intersect, you find the richest clusters of galaxies, massive concentrations of hundreds or thousands of galaxies bound together by their mutual gravity. These clusters mark the nodes of the web, the places where the most matter has accumulated. Our own local group, by comparison, is barely a whisper of density, a minor eddy in the cosmic flow. Between the filaments lie the voids, and they make up the majority of the universe's volume. While filaments and clusters might seem impressive because they contain all the visible matter, it's the voids that truly dominate space. Roughly 80% of the universe's volume is taken up by these regions of near emptiness. If you were to choose a random point in space, you would most likely find yourself in a void, far from any galaxy. The cosmic web, seen from this perspective, is mostly emptiness with occasional threads of matter running through it. What's fascinating is that the cosmic web is not static. It continues to evolve as gravity does its work. Voids are slowly growing larger as matter drains from them into the surrounding filaments. Filaments are gradually condensing, their galaxies flowing along them toward the densest clusters. Over cosmic time, the web becomes more pronounced, the contrast between empty and full regions growing starker. Tens of billions of years from now, the cosmic web will be even more dramatic than it is today, with voids expanding and filaments thinning as matter concentrates in fewer, denser nodes. This evolution connects to something I find deeply fascinating, which we'll explore next. The cosmic web is not just a passive backdrop for galaxies. It actively shapes how galaxies form, how they evolve, and even whether they can form stars. And understanding this influence requires us to look more closely at what exists, or rather what doesn't exist, inside the voids themselves. When we say a cosmic void is empty, we need to be careful about what that word means. Voids are not complete vacuums devoid of all matter. Rather, they're regions where the density of galaxies is far lower than average, where a typical region of space might contain 1 galaxy per cubic megaparsec. A void might contain 1 galaxy per 10, or even 100 cubic megaparsecs. The difference is dramatic, but it's not absolute emptiness. The galaxies that do exist in voids tend to be different from galaxies elsewhere. They're typically smaller, dimmer, and contain more gas relative to stars. Many are dwarf galaxies, faint collections of stars and gas that would be unremarkable neighbours to larger galaxies, but become notable simply because they exist in such isolated conditions. These void galaxies are some of the loneliest objects in the universe, separated from their nearest neighbours by tens of millions of light-years of nearly empty space. If you lived in a galaxy deep inside a void, your night sky would be profoundly dark, with perhaps a handful of faint smudges visible even with powerful telescopes. Between the rare galaxies and voids lies the intergalactic medium, a thin soup of gas that pervades all of space. Even in the densest cosmic regions, this gas is incredibly tenuous, far more rarefied than the best vacuum we can create on Earth. In voids, the intergalactic medium is even thinner, but it's not entirely absent. It exists as ionized hydrogen and helium, the simplest elements, heated to temperatures of thousands or even millions of degrees by radiation from distant galaxies and by the cosmic microwave background itself. This brings us to dark matter, the invisible substance that makes up most of the universe's mass. Dark matter doesn't emit light or interact with normal matter except through gravity, which makes it extraordinarily difficult to study. But computer simulations of cosmic structure, based on our understanding of dark matter's properties, suggest that even voids contain dark matter. The distribution is much less dense than in filaments or clusters, but dark matter forms a faint web even in the emptiest regions. These dark matter halos might serve as the skeletons around which the few void galaxies formed. Voids aren't as empty as they appear. Voids aren't as empty as they appear simply because we can't see everything they contain. Dark galaxies, if they exist, would be clouds of gas that never formed stars, remaining dark and invisible to our telescopes. Failed galaxies, regions where conditions almost allowed galaxy formation but ultimately fell short, might lurk in voids as faint wisps of matter we haven't yet detected. Our current technology allows us to see only the brightest objects, which means the sensors of void contents remains incomplete. What we call empty might simply be what we cannot yet see. The temperature and density of matter in voids also affect cosmic evolution in subtle ways. The intergalactic medium in voids is heated by cosmic rays and radiation from the first generations of stars that formed billions of years ago. This heating prevents new gas from cooling and collapsing to form stars, which helps explain why voids remain relatively empty over time. Once a region becomes underdense, the conditions within it tend to maintain that underdensity, creating a feedback loop that preserves the void structure over billions of years. Which leads us naturally to consider how these voids came to exist in the first place, and why the universe chose this particular architecture of matter and emptiness. The answer involves both the large-scale dynamics of cosmic expansion and the quantum fluctuations that existed in the first fraction of a second after the Big Bang. The seeds of cosmic voids were planted in the first moments of the universe, long before galaxies existed. In the era of cosmic inflation, a period lasting perhaps 1/trillionth of a trillionth of a second, the universe expanded faster than the speed of light, stretching quantum fluctuations to cosmic scales. These fluctuations were variations in energy density so slight that they would have been invisible even if anyone had been there to observe them. But they were enough. When inflation ended and the universe settled into a more sedate expansion, pulled matter toward themselves more effectively than their surroundings. Over millions of years, this attraction amplified the initial density difference. Dense regions grew denser, pulling in gas and dark matter from neighbouring areas. The regions that were slightly less dense lost matter to their denser neighbours, becoming increasingly underdense. This is the essential mechanism of structure formation, a process driven entirely by gravity acting on the remnants of quantum fluctuations from the universe's first instant. By the time the first stars began to form, a few 100 million years after the Big Bang, the cosmic web was already taking shape. Dark matter had clumped into filaments and nodes, creating gravitational wells where normal matter could collect. Between these concentrations, vast regions remained relatively empty, their matter having drained away to feed the growing structures. These proto-voids were smaller and less empty than the voids we see today, but they represented the same basic pattern. Bubbles of underdensity surrounded by walls and filaments of overdensity. As the universe continued to expand, the voids expanded with it. This is crucial to understand. Cosmic expansion affects everything, but it affects empty regions differently than dense ones. In dense regions, gravity is strong enough to resist expansion, holding galaxies together within clusters and filaments. Tracking, or even slightly exceeding the tracking, or even slightly exceeding the overall cosmic expansion rate. What began as modest underdensities became enormous bubbles of near emptiness as billions of years passed. There's also a dynamic process at work that helps voids maintain their emptiness. Any galaxy that forms inside or near a void feels the gravitational pull of the denser regions surrounding it. Over time, this pull can draw void galaxies outward, toward the walls of the void where matter is more concentrated. Computer simulations show this migration clearly, with galaxies drifting like leaves in a current, moving from emptier regions toward fuller ones. The voids effectively repel galaxies not through any force pushing outward, but through the stronger gravitational attraction of matter surrounding them pulling inward. The cosmic microwave background, the afterglow of the Big Bang, provides evidence for this history. When we map the tiny temperature variations in this ancient light, we see the fingerprint of those original density fluctuations. The pattern matches with remarkable precision the distribution of matter we observe in the cosmic web today. The hot spots in the cosmic microwave background correspond to regions that became filaments and clusters, while the cold spots mark the locations of future voids. The universe, in a sense, revealed its architectural plans in that ancient light, and we're living in the building those plans described. And this brings us to something equally important to understand. Voids are not aberrations or flaws in cosmic structure. They're as fundamental to the universe as galaxies themselves, natural consequences of how gravity organizes matter on the larger scales. To understand why our universe looks the way it does, we need to understand voids just as much as we need to understand clusters and superclusters. Voids come in many sizes and shapes, though calling any cosmic structure a particular shape requires some interpretation. The largest voids span hundreds of millions of light-years across, while smaller ones might be only 20 or 30 million light-years in diameter. Most voids are roughly spherical or ellipsoidal, their shapes determined by the distribution of matter surrounding them and the history of how they formed and grew. But perfect spheres are rare. Gravity, cosmic flows, and the interactions between neighbouring voids create irregularities, bulges, and elongations that give each void its own character. Some voids are remarkably isolated, surrounded on all sides by dense walls of galaxies and clearly separated from neighbouring voids. These are the easiest voids to identify and study because their boundaries are well defined. You can point to a region and say with confidence that this is void and this is not. Other voids merge together, their boundaries overlapping or touching, creating vast complexes of emptiness that can stretch across significant fractions of the observable universe. The distinction between one void and another becomes somewhat arbitrary in these regions, a matter of definition rather than physical separation. The boundaries of voids are where most of the action happens. These are the regions where voids meet filaments, where underdense regions transition to overdense walls. Galaxies in void walls experience complex gravitational influences, pulled both by the dense matter around them and by the relative emptiness of the void itself. These galaxies often show signs of interaction and merger, suggesting that void boundaries are dynamic, active regions despite being far from the densest cosmic structures. The walls themselves form sheets and filaments, creating a kind of shell around the void's interior. There's a hierarchical nature to voids that mirrors the hierarchical nature of cosmic structure generally. Just as galaxies cluster into groups, groups into clusters, and clusters into superclusters, voids also organize at multiple scales. Small voids exist within larger underdense regions, which themselves are embedded in even larger structures. This self-similarity across scales is a fundamental property of cosmic architecture, suggesting that the same physical processes operate at all levels, from the smallest density fluctuations to the largest cosmic structures. Measuring voids precisely is challenging work. Astronomers must map the three-dimensional positions of millions of galaxies, identifying regions where galaxy density drops significantly below average. Different surveys use different criteria for what counts as a void, which means that catalogues of voids from different teams don't always agree perfectly. A void identified in one survey might be split into several smaller voids in another survey, or vice versa. This isn't sloppiness, but rather reflects the genuine ambiguity in drawing boundaries around underdense regions. The universe doesn't label its structures for us. The shapes and sizes of voids encode information about cosmic history. By studying the distribution of void sizes, astronomers can test models of structure formation and constrain properties of dark matter and dark energy. If voids were significantly different in size or shape than predicted by our models, it would suggest something fundamental was wrong with our understanding of cosmic evolution. So far, observed voids match predictions reasonably well, which gives us confidence that we understand at least the broad outlines of how structure forms. But there are anomalies and puzzles, hints that our picture might be incomplete. This statistical approach to understanding voids connects to something we'll explore more deeply soon. Individual voids are interesting, but what they tell us about the universe comes from studying populations of voids across cosmic time, seeing how they evolve and what patterns emerge. And one of the most important discoveries about voids is that their properties have been changing as the universe ages, growing larger and emptier as dark energy drives cosmic acceleration. Discovering voids requires a peculiar kind of observation. You cannot take a photograph of emptiness. Instead, astronomers must map where galaxies are and infer where they are not. This seems straightforward enough, but the practical challenges are enormous. Galaxies are faint, distant, and numerous. Creating a three-dimensional map of their positions requires measuring not just their locations on the sky, but their distances from us, which means determining their redshifts, a painstaking process even with modern technology. The first hints of large-scale structure came in the 1970s, when astronomers began measuring redshifts for hundreds of galaxies. They noticed that galaxies seemed to cluster together, with regions of apparent emptiness between the clusters. But without enough data to map these patterns in 3 dimensions, it was unclear whether they were seeing real cosmic structure or just statistical flukes. The breakthrough came with dedicated galaxy surveys that measured tens of thousands of redshifts, enough to reveal genuine large-scale patterns. The Center for Astrophysics Redshift Survey, completed in the early 1980s, produced the first clear image of the cosmic web. When astronomers plotted the positions of galaxies in a thin slice of the sky, extending outward in distance, they saw something remarkable. Galaxies formed long chains and clusters surrounding enormous empty regions. One of these regions, quickly dubbed the Beauty Void, stretched more than 300 million light-years across. It was a revelation. The universe had structure on scales far larger than anyone had anticipated, and much of that structure consisted of places where galaxies simply weren't. Modern surveys have refined this picture dramatically. Projects like the Sloan Digital Sky Survey have mapped millions of galaxies, creating three-dimensional atlases of cosmic structure with unprecedented detail. These surveys reveal voids throughout the nearby universe. From small 20 million light-year bubbles to massive structures several times larger, each void is catalogued, its size and shape recorded, its contents inventoried. The result is a census of cosmic emptiness, a map of where the universe has chosen not to place its matter. But mapping nearby voids is only part of the story. Astronomers also want to understand how voids have evolved over cosmic time, which means looking at very distant voids as they existed billions of years ago. Light from distant galaxies takes billions of years to reach us, so when we observe those galaxies, we see them as they were in the past. By mapping the distribution of galaxies at different distances, astronomers can trace the history of voids, watching them grow and evolve as the universe expands and ages. This historical perspective reveals that voids were smaller and less empty in the past. Billions of years ago, the underdense regions that would become today's voids contained more galaxies and had less dramatic density contrast with their surroundings. The process of void growth is ongoing, driven by cosmic expansion and the continued migration of matter from underdense to overdense regions. Understanding this evolution helps cosmologists test their models of how structure forms and evolves under the influence of gravity and dark energy. There's also the challenge of identifying voids at the highest redshifts, in the early universe when the first galaxies were just forming. At these distances, galaxies are incredibly faint and difficult to detect, which makes mapping large-scale structure extraordinarily challenging. But even with limited data, astronomers have identified hints of underdense regions in the early universe. Proto-voids that would eventually grow into the enormous empty structures we see today. These observations push the limits of current technology and hint at what next-generation telescopes might reveal. Which brings us naturally to consider what all this mapping tells us about the nature of voids themselves, and whether they're truly as empty as they appear, or whether we're simply missing something in our observations. The more precisely we measure voids, the more complicated they become. What initially appeared to be simply empty regions turn out to have structure and properties that challenge our understanding. Some voids contain more galaxies than expected. Others show unexpected asymmetries or alignments. A few display characteristics that don't quite match theoretical predictions. These anomalies don't overturn our basic picture of cosmic structure, but they suggest that voids are more complex than simple bubbles of emptiness. One persistent question involves what astronomers call the void phenomenon. This refers to the observation that some very faint small galaxies exist deep inside voids, far from any significant concentration of matter. These galaxies shouldn't exist according to simple models of structure formation. In such isolated environments with so little matter around them, it's unclear how these galaxies gathered enough gas to form stars, or how they avoided being pulled toward denser regions over billions of years. Their existence suggests there's something about galaxy formation in voids that we don't fully understand. The galaxies that do inhabit voids also tend to be actively forming stars, which is somewhat surprising. In denser environments, galaxies often stop forming stars as they collide with neighbours, or as their gas is stripped away by the hot gas pervading galaxy clusters. But void galaxies, isolated from these environmental effects, continue forming stars at rates that can be higher than similar galaxies in denser regions. This has led some astronomers to suggest that voids might be the last refuges, where certain types of galaxies can continue evolving undisturbed, preserving modes of star formation that have ceased elsewhere. There's also the curious question of void alignments. When astronomers measure the shapes and orientations of voids, they find that neighbouring voids tend to be aligned with each other and with the filaments surrounding them. This isn't random. It reflects the fact that voids, filaments and clusters all formed from the same initial density fluctuations and have evolved under the same gravitational influences. The cosmic web is coherent, with structures at all levels showing coordinated patterns, but some observed alignments seem stronger than models predict, hinting at physical processes we haven't fully accounted for. Another puzzle involves the so-called cold spot in the cosmic microwave background. This is an unusually large cold region in the sky that some researchers have suggested might be the signature of an enormous supervoid between us and the early universe. If a truly massive void exists in that direction, the cosmic microwave background light passing through it would be affected in ways that could create the observed cold spot. However, this explanation remains controversial, with some studies supporting it and others finding insufficient evidence for such a large void. The question remains open. Then there's the issue of what dark matter does in voids. We know dark matter must exist in underdense regions because gravitational lensing studies show matter deflecting light, even in areas with few visible galaxies. But the precise distribution of... Before we continue, I want to pause for just a moment, because what you have learned in the last 30 minutes is something genuinely rare. Most people move through their entire lives without ever stopping to understand the world at this level, but you did. Tonight you chose curiosity over noise and depth over distraction. That is exactly who this channel was made for. If you want to keep being that person, a like and subscribe takes 2 seconds and make sure this channel never stops finding you. Now, let's go deeper. But the precise distribution of dark matter in voids is uncertain. Does it form smooth halos? Or does it clump into structures too small to host visible galaxies? How much dark matter exists in voids compared to filaments? These questions matter because dark matter makes up most of the universe's mass, and understanding its distribution means understanding the true structure of space. Some researchers have proposed that voids might contain exotic forms of matter or energy that we haven't detected yet. Perhaps some fraction of dark energy is clumped in voids, rather than being uniformly distributed. Perhaps there are populations of failed galaxies or dark galaxies that contain matter but no stars. Perhaps magnetic fields or cosmic rays are more important in voids than we've assumed. These ideas remain speculative, but they reflect the fact that empty regions of space are difficult to study and might harbour surprises. This uncertainty about what voids truly contain leads us to consider how living in or near a void affects our observations of the universe, and whether our particular cosmic location has biased our understanding of cosmic structure in ways we need to account for. Living on the edge of the local void means we have a particular perspective on the universe, one that might differ from the view you'd get from other cosmic locations. This isn't about anything mysterious or exotic. It's simply that the distribution of matter around us affects how we observe distant structures and measure cosmic properties. Understanding our cosmic environment is essential for interpreting our observations correctly. The local void creates an asymmetry in the matter distribution around us. In some directions, we look through relatively empty space, seeing distant galaxies with less intervening matter to obscure or distort their light. In other directions, we look through denser regions, with more galaxies between us and the distant universe. This asymmetry affects observations in subtle ways. It influences how we measure cosmic expansion rates, how we detect gravitational lensing, and how we interpret the distribution of galaxies at various distances. One effect is on our measurements of the Hubble constant, the rate at which the universe is expanding. Different measurement techniques have yielded slightly different values for this fundamental cosmic parameter, a discrepancy known as the Hubble tension. Some researchers have suggested that our location near a void could bias our local measurements in ways that contribute to this tension. If we're in an underdense region that's expanding slightly faster than the cosmic average, our local measurements might not perfectly match measurements based on the early universe. This idea remains controversial, with some studies supporting it and others finding the effect too small to explain the full tension. The void also affects the peculiar velocities of galaxies around us. Peculiar velocity is the motion of a galaxy due to gravity, separate from its motion due to cosmic expansion. Galaxies near voids tend to move away from the void and toward denser regions, creating organised flows of matter on very large scales. Our own local group participates in these flows, moving at hundreds of kilometres per second toward the Virgo cluster and other concentrations of matter. Understanding these motions helps us map the distribution of matter, both visible and dark, in our cosmic neighbourhood. Gravitational lensing provides another window into how voids affect our view. When light from distant galaxies passes through or near massive structures, its path bends due to gravity, creating distortions we can measure. Voids, being underdense, create negative lensing effects, subtle but detectable. By studying how light from distant objects is affected as it passes through voids, astronomers can map the matter distribution in these supposedly empty regions, revealing the faint web of dark matter that persists even where visible galaxies are absent. Our location also affects cosmic surveys in practical ways. When we map the universe, we start from our position and work outward, measuring distances and positions relative to ourselves. Any systematic effect that depends on direction will show up in our maps. The local void creates such a directional dependence. Surveys looking through the void see fewer nearby galaxies and might reach greater depths more easily, while surveys looking toward denser regions encounter more foreground objects. Accounting for these effects requires careful analysis and an understanding of our local cosmic environment. There's something humbling about recognizing that our cosmic address affects our observations. We're not observing the universe from some neutral average position, but from a specific location with its own characteristics and biases. This doesn't invalidate our measurements, but it means we must be careful about extrapolating from local observations to cosmic conclusions. What we see from here might not be perfectly representative of what you'd see from elsewhere in the universe, and yet there's also something encouraging about this recognition. The fact that we can identify our location's influence on our observations, measure it, and correct for it demonstrates the power of the scientific method. We can account for our cosmic context, teasing apart local effects from universal properties. This leads us to consider what voids tell us about the universe more broadly, and how studying these empty regions helps us understand cosmic evolution. Dark energy, the mysterious force accelerating the universe's expansion, has its most dramatic effects in the emptiest regions of space. In dense areas where gravity is strong, dark energy's repulsive influence is overwhelmed by matter's gravitational attraction, but in voids, where matter is sparse, dark energy dominates. This makes voids particularly useful laboratories for studying dark energy's properties and effects. The acceleration of cosmic expansion was discovered in the late 1990s through observations of distant supernovae. These exploding stars are bright enough to be seen across billions of light years, and their brightness reveals their distance. By comparing distances with redshifts, astronomers discovered that the universe's expansion is speeding up, not slowing down as gravity alone would predict. This acceleration requires something with negative pressure, an energy that fills space and pushes it apart. We call this dark energy, though we don't know what it actually is. Voids are growing larger as a direct consequence of dark energy. In a universe without dark energy, voids would still expand due to cosmic expansion, but that expansion would gradually slow over time as gravity worked to pull everything back together. With dark energy, expansion accelerates, and voids grow increasingly large and empty. The rate at which voids expand provides a measurement of dark energy's strength, offering an independent check on measurements made using other techniques. Computer simulations of cosmic structure that include dark energy show voids becoming more prominent over time. In the early universe, matter and dark energy were roughly comparable in their influence on cosmic dynamics. As the universe expanded, matter became more dilute while dark energy remained constant in density, causing dark energy to gradually dominate. This transition happened several billion years ago, around the time Earth was forming. Since then, dark energy has been driving accelerated expansion, making voids grow faster and emptying them more completely. The properties of dark energy can be tested by studying how voids evolve. If dark energy is simply Einstein's cosmological constant, a property of space itself with constant density, voids should evolve in a specific, predictable way. If dark energy is something more exotic, something that changes with time or varies from place to place, void evolution might differ from predictions. So far, observations match the cosmological constant model reasonably well, but measurements are still not precise enough to rule out more complex alternatives entirely. There's also the question of whether dark energy is perfectly uniform, or whether it might be slightly concentrated in certain regions. Most models assume dark energy is the same everywhere, but this assumption could be wrong. If dark energy were somehow enhanced in voids, it would affect their expansion rates and properties in measurable ways. Looking for such effects is challenging because any signal would be subtle, but the possibility keeps researchers interested in precise measurements of void characteristics. Some cosmologists have proposed that voids might help explain cosmic acceleration without invoking dark energy at all. These models, called back-reaction models, suggest that the complex structure of matter in the universe creates expansion rates that vary from place to place. Voids expand faster than dense regions, and averaging over these different rates might create an apparent acceleration. While most cosmologists remain skeptical of these ideas, they highlight how voids are central to understanding cosmic expansion. The future evolution of voids depends on dark energy's ultimate nature. If dark energy remains constant, voids will continue growing indefinitely, becoming increasingly large and empty as the universe ages. Eventually, in the far future, voids might make up almost all of the universe's volume, with matter concentrated in ever smaller, more isolated clusters. But if dark energy changes or decays over time, void evolution might take different paths. Understanding dark energy means understanding the future of cosmic structure itself, which brings us to contemplate something both fascinating and slightly melancholic. The universe is becoming increasingly dominated by emptiness, with matter gathering into smaller, denser islands surrounded by growing oceans of void. Our cosmic future is one of isolation and dispersion, a theme we'll explore as we continue deeper into this slow drift through cosmic architecture. Imagine the universe 10 billion years from now, 100 billion years from now, a trillion years into the future. If dark energy continues driving accelerated expansion as it does today, the cosmic web will become increasingly sparse. Voids will dominate space, growing so large that entire superclusters of galaxies become isolated islands surrounded by emptiness vast beyond current comprehension. This is not speculation, but a natural consequence of the cosmic dynamics we observe. The galaxies that remain gravitationally bound to each other will merge over time, forming larger and larger structures. Our local group, for instance, will eventually become a single massive elliptical galaxy, as the Milky Way and Andromeda merge and absorb their smaller companions. This merged galaxy will be an island, surrounded by voids that have grown to span billions of light years. The nearest neighbour galaxies, which today are tens of millions of light years away, will have receded to distances so great that their light will be redshifted beyond detectability. In the far future, an astronomer living in our merged galaxy would have a profoundly different view of the universe than we have today. Looking out in any direction, they would see darkness. The cosmic microwave background would have cooled and stretched to such long wavelength that it would be undetectable. distant galaxies would have receded beyond the cosmic horizon. The distance at which expansion carries them away faster than light can travel toward us. The observable universe would consist solely of the local merged galaxy, floating alone in an ocean of darkness. This astronomer would face an epistemological challenge. With no view of distant galaxies, no cosmic microwave background to study, and no evidence of cosmic expansion accessible to their observations, would they be able to discover that they lived in an expanding universe? Would they know about the Big Bang, about dark energy, about the vast cosmic structures that once existed? Or would they conclude that the universe consisted only of their island galaxy, eternal and unchanging in an infinite void? The universe would have erased its own history. Some cosmologists have suggested that we might already be in a similar situation, unable to see evidence of cosmic structures or processes that existed before our observable universe came into being. Just as future astronomers might find no evidence of today's cosmic web, perhaps we can't see evidence of structures from earlier phases of cosmic history. This idea is speculative, but highlights how much our understanding of the universe depends on our particular cosmic moment, our specific place in the timeline of existence. The far future of voids also raises questions about the ultimate fate of matter itself. If protons decay, as some theories of particle physics suggest, even the atoms making up stars and planets will eventually disintegrate. In a universe dominated by growing voids and decaying matter, the final state might be one of almost perfect emptiness, with only radiation and perhaps exotic particles remaining. The cosmic web, once a grand architecture of matter and light, would dissolve into a homogeneous darkness. But there's also a perspective that finds beauty in this future. The universe will not end in a catastrophic collapse, but will instead gently expand and cool, gradually transitioning from complexity to simplicity. The processes that created stars, galaxies, and perhaps life will run their course and end, but peacefully, without violence. The voids that seem empty to us are simply the early stages of the universe's ultimate destiny, regions that have already embraced the future that awaits all of space. This contemplation of cosmic futures connects to something important about how we understand our place in time as well as space. We exist at a moment when the universe is still rich with structure, when galaxies populate the cosmic web and voids are large but not yet dominant. This is not a privileged moment in any absolute sense. But it is a particular one, a time when the universe displays a balance between matter and emptiness that will not last forever. Understanding how voids form and evolve requires more than observation. Astronomers use powerful computer simulations to model the entire history of cosmic structure formation, from the early universe to today. These simulations begin with the density fluctuations present shortly after the Big Bang and follow how gravity amplifies them over billions of years. The result is a virtual universe that can be compared with the real one, testing whether our theories truly explain what we observe. The simulation starts simple, at least conceptually. You initialize a cube of virtual space, filling it with particles that represent dark matter. You assign these particles initial positions and velocities based on the density fluctuations predicted by models of the early universe. Then you let gravity do its work, calculating how each particle affects every other particle and evolving the system forward in time. After billions of simulated years, you examine the final distribution of matter and compare it to the observed cosmic web. In practice, these simulations are extraordinarily complex. Modern versions track billions or even trillions of particles, requiring supercomputers running for months to complete a single simulation. They must account for both dark matter and normal matter, each of which behaves differently. Dark matter interacts only through gravity, but normal matter can heat, cool, form stars, and create feedback effects that influence large-scale structure. Including all these processes accurately is a tremendous computational challenge. The simulations produce cosmic webs that look remarkably similar to what we observe. Filaments emerge naturally, connecting dense nodes where galaxy clusters form. Between the filaments, voids appear, growing larger as the simulation progresses. The statistical properties of simulated voids, their sizes, shapes, and abundance, match observed voids reasonably well. This agreement gives cosmologists confidence that the basic story of structure formation is correct, that gravity acting on initial density fluctuations can indeed produce the universe we see. But simulations also reveal details that observations alone cannot provide. They show how individual particles move through the cosmic web, flowing from voids into filaments and eventually into clusters. They track the temperature and density of gas in different environments, predicting where stars should form and where they shouldn't. They follow the evolution of voids over time, showing how they expand, merge, and interact. These predictions can then be tested against observations, refining our understanding of cosmic processes. One particularly interesting application of simulations involves testing different models of dark energy. By running simulations with various assumptions about dark energy's properties, cosmologists can see how void evolution changes. A universe with more dark energy produces larger voids that grow faster. A universe with dark energy that changes over time produces different patterns of void growth than one with constant dark energy. Comparing these predictions to observed void properties helps constrain what dark energy might be. Simulations also help identify rare objects and events. For instance, they predict that occasionally two large voids should merge together, creating a momentary disturbance in the cosmic web structure. These mergers should be detectable through their effects on galaxy distributions and peculiar velocities. Finding such events in real observations would confirm simulation predictions and provide insights into void dynamics that are difficult to obtain otherwise. There are limitations, of course. Simulations must make approximations to be computationally feasible. They might not resolve small-scale structures adequately, or might oversimplify certain physical processes. The agreement between simulations and observations is good, but not perfect, and the discrepancies might point to missing physics or incorrect assumptions. But overall, simulations are powerful tools that complement observations, helping us understand the mechanisms driving cosmic evolution. And this computational approach connects naturally to one of the most fundamental questions about voids. How do they affect the galaxies that exist within or near them? The answer involves both the large-scale flows we've discussed and the local environments where stars actually form. Galaxies are shaped by their environments in profound ways. A galaxy living in a dense cluster experiences frequent interactions with neighbours, gravitational harassment, and encounters with hot intergalactic gas. These experiences transform the galaxy, stripping away gas, triggering or quenching star formation, and altering its structure. But a galaxy in a void lives a very different life, one characterised by isolation and slow, undisturbed evolution. Void galaxies tend to be gas-rich. Without neighbours to strip away their gas or mergers to consume their reservoirs, they retain the hydrogen and helium needed to form new stars. Observations show that many void galaxies are actively forming stars, sometimes at rates comparable to or higher than similar galaxies in denser environments. This is somewhat counterintuitive. You might expect isolated galaxies to run out of gas eventually, but they seem to continue forming stars for billions of years. The explanation involves how galaxies acquire gas. Even in voids, there's a tenuous intergalactic medium, and galaxies can slowly accrete this gas over time. Additionally, void galaxies might have started with larger gas reservoirs, having formed in regions where gas wasn't stripped away by early energetic processes. Their isolation preserves these reservoirs, allowing star formation to continue long after similar galaxies in denser regions have exhausted their fuel. The structures of void galaxies also differ from their counterparts elsewhere. Many are late-type spirals, Galaxies with prominent disks and ongoing star formation. Early-type galaxies. The ellipticals and lenticulars that dominate dense clusters are relatively rare in voids. This distribution reflects different evolutionary pathways. In dense environments, mergers and interactions transform spirals into ellipticals. In voids, such interactions are exceedingly rare, so spirals can persist unchanged for cosmic timescales. There's also evidence that void galaxies rotate differently. The angular momentum of galaxies, their spin, is influenced by tidal forces from nearby structures during formation. Void galaxies, forming in regions with fewer tidal influences, might have different spin distributions than galaxies elsewhere. Some studies suggest void galaxies tend to have their spins aligned with the large-scale structure around them, particularly the walls of their parent voids. This alignment would be another fingerprint of their unique environmental history. The stellar populations in void galaxies show interesting characteristics as well. Because these galaxies form stars continuously over long timescales, they contain a mix of old and young stars. The young stars provide bright blue and ultraviolet light, while older stars contribute red and infrared light. The combination gives void galaxies distinctive spectra that can be identified in surveys, helping astronomers find and study these isolated objects. However, not all void galaxies are actively forming stars. Some are quenched, their star formation shut down despite having no obvious neighbours to blame for the quenching. Understanding why these galaxies stopped forming stars is an active area of research. Perhaps they exhausted their gas supplies. Perhaps feedback from previous generations of stars heated their remaining gas beyond the point where it could collapse. Perhaps some process related to dark matter halos plays a role. The answers remain uncertain. The supermassive black holes at the centres of galaxies also reflect environmental differences. In dense environments, galaxy mergers can fuel black hole growth, creating active galactic nuclei that shine brightly across the electromagnetic spectrum. Void galaxies, lacking frequent mergers, should have less active black holes on average. Observations generally confirm this expectation, though exceptions exist. Some void galaxies harbour surprisingly active black holes, suggesting that processes other than mergers can feed these cosmic engines. All these differences matter for understanding galaxy evolution as a universal process. If galaxies evolve differently in voids than in dense regions, then a complete theory of galaxy formation must account for environmental effects across the full range of cosmic densities. Voids are not just empty spaces, but laboratories for studying galaxy evolution in the absence of external disturbances, revealing what galaxies do when left largely alone. This exploration of isolated galaxy evolution leads us to consider whether life itself might be affected by cosmic location, and whether existing in or near a void has any implications for habitability, not just of individual planets, but of regions of the universe. The question of whether our cosmic location affects the emergence of life is subtle and speculative, but worth contemplating. On one hand, life as we know it depends on planetary conditions, stellar properties, and chemistry, none of which seem directly connected to whether a galaxy sits in a void or a filament. On the other hand, galactic evolution, star formation rates, and heavy element production all vary with environment, which could indirectly influence habitability. Void galaxies, being gas-rich and actively forming stars, produce new generations of stars continuously. Each generation synthesizes heavy elements: carbon, oxygen, nitrogen, silicon, iron, the building blocks of planets and life. Over billions of years, void galaxies enrich their interstellar medium with these elements, providing the raw materials for terrestrial planets and organic chemistry. In this sense, void environments might be conducive to life, maintaining conditions for ongoing planet formation over extended timescales. However, isolation might have downsides. The rate at which supernovae occur in a galaxy affects both the production of heavy elements and the radiation environment. Too few supernovae and heavy elements remain scarce. Too many, and radiation might sterilize planets or disrupt planetary systems. Void galaxies, with their steady but relatively modest star formation rates, might hit a sweet spot, producing enough supernovae to enrich the interstellar medium without creating an overly hazardous radiation environment. There's also the question of galactic habitability over cosmic time. In dense environments, galaxy mergers and interactions can trigger starbursts, brief periods of intense star formation that produce many massive short-lived stars. These events create waves of supernovae that might make parts of galaxies temporarily inhospitable to life. Void galaxies, evolving more peacefully, might maintain more stable conditions over longer periods, potentially favouring the emergence and persistence of life. Some researchers have speculated about the role of cosmic rays in this equation. Cosmic rays are high-energy particles that pervade galaxies, produced by supernovae and other energetic events. They can damage DNA and pose hazards to life, but they also might play roles in atmospheric chemistry and even evolution. The cosmic ray environment in void galaxies could differ from that in denser regions, depending on star formation histories and magnetic field structures. Whether this difference favours or hinders life remains unclear. The anthropic principle enters these discussions as well. This principle suggests that we observe the universe from a location compatible with our existence, which might not be a random location. If life requires certain environmental conditions, and those conditions are more common in particular cosmic environments, then we should not be surprised to find ourselves in such an environment. Our location near the local void might be a consequence of void-adjacent regions being particularly favourable for life, though this argument remains highly speculative. There's also the intriguing possibility that voids affect the probability of civilizations detecting each other. In a dense region of space, a technological civilization might find nearby civilizations more easily, simply because more habitable planets exist within a given distance. In voids, the vast distances between galaxies would make detection of extraterrestrial intelligence far more difficult. If we're in a void-adjacent region, this could partially explain why we haven't detected signals from other civilizations. They simply might be too far away for current technology to detect. None of this is settled science. We have one example of life on Earth, in one galaxy, the Milky Way, near one void, the local void. Drawing conclusions from a sample size of one is inherently problematic. But these considerations highlight how cosmology and astrobiology might connect, how the largest structures in the universe could, through indirect pathways, influence the emergence and evolution of life. And thinking about life in cosmic context leads us to contemplate our observations of the universe more philosophically. What does it mean that we find ourselves in this particular cosmic location, at this particular cosmic time? Is there significance to our address, or is it merely an accident of circumstances beyond meaning? There's a human tendency to seek significance in circumstances, to imagine that where we are has meaning beyond mere chance. Cosmologists must resist this tendency, while simultaneously acknowledging that our cosmic location does affect our observations and potentially our existence. Balancing these perspectives requires care. The fact that we exist near a void is, in one sense, entirely unremarkable. Voids and void-adjacent regions make up a substantial fraction of the universe's volume. Location in the universe that could host location in the universe that could host observers, void-adjacent regions would be among the possible results, neither particularly rare nor particularly common. Yet there's also the consideration that not all cosmic locations are equally conducive to observations. A civilization arising deep inside a giant elliptical galaxy in a dense cluster might face challenges we don't encounter. Their sky would be crowded with neighbouring stars, making distant observations difficult. Their galaxies' interactions might create a hazardous radiation environment. Their location might bias their observations of cosmic expansion or structure in ways harder to correct than our biases. From this perspective, our location might be convenient for doing cosmology, even if not deliberately selected. This connects to a version of the anthropic principle sometimes called the observation selection effect. We necessarily find ourselves in a location compatible with making observations, because we wouldn't exist in locations where conditions prevented our emergence. If certain cosmic environments are more favourable for the emergence of observers, those observers will disproportionately find themselves in such environments, even if those environments are not the most common type in the universe. Some cosmologists take this reasoning further, suggesting that our observations might be systematically biased by selection effects we haven't fully recognised. Perhaps the universe looks a certain way to us precisely because we're observers of a particular type in a particular environment. A different type of observer in a different environment might observe a universe with seemingly different properties, not because the universe itself differs, but because their observational context differs from ours. These ideas venture into philosophy as much as science. They're difficult to test because we have only our own observations to work with. We can't compare notes with observers in fundamentally different cosmic environments to see whether they observe different universes. But the considerations remind us that our picture of the cosmos is always a view from somewhere, shaped by our location and nature as much as by the universe's intrinsic properties. There's also a temporal aspect to consider. We exist at a particular moment in cosmic history, roughly 14 billion years after the Big Bang, when the universe is expanding and accelerating, but before it becomes dominated by voids. Observers arising billions of years in the future would see a very different universe. Observers from the distant past would have seen a younger, denser cosmos. Our temporal location affects our observations as much as our spatial location. Some researchers have suggested that the current epoch might be particularly favourable for understanding the universe. We're far enough from the Big Bang to have clear skies and stable conditions for complex observations, but not so far into the future that evidence of cosmic evolution has been erased. The cosmic microwave background is still visible, distant galaxies are still observable, and cosmic structure is neither too subtle nor too extreme. Perhaps observers in the universe tend to emerge during this particular window of cosmic history, making our temporal location less random than it might appear. Of course, this is speculation built upon speculation. We don't know whether other observers exist when they might have emerged, or what conditions are truly necessary for observation. But contemplating these questions helps clarify what we can learn from our observations and what might remain forever beyond our reach due to our particular cosmic context. What's certain is that we do exist here and now, in this specific cosmic location at this specific cosmic time. Our task as observers is to understand how our context affects our measurements, correct for those effects where possible, and acknowledge the limits of what we can determine from our particular vantage point. The universe we observe is real, but it's also a universe observed from Earth, from the Milky Way, from the edge of the local void in the early 21st century. That specific perspective shapes everything we see, and recognizing this specificity leads us back to considering what voids themselves tell us about cosmic principles that might transcend any particular observational context, fundamental truths that remain true regardless of where or when you observe them. Despite the complexities and uncertainties we've explored, voids do reveal fundamental truths about how the universe works. Gravity acts on all scales, from planets to galaxy clusters to cosmic voids. The same physical laws that govern falling apples also govern the motions of galaxies and the expansion of voids. This universality of physical law is one of science's deepest assumptions, and voids provide tests of whether that assumption holds on the larger scales. The formation and evolution of voids directly demonstrate how gravity amplifies tiny initial fluctuations into dramatic structures. We can't watch this process in real time, as it takes billions of years, but we can observe voids at different distances and therefore different times in cosmic history, effectively watching a time-lapse of structure formation. The agreement between these observations and theoretical predictions confirms that gravity behaves as expected across cosmic scales. Voids also teach us about dark matter. We cannot see dark matter directly, but we can infer its presence through gravitational effects. In voids, where visible matter is sparse, dark matter's gravitational influence becomes particularly important. The shapes and evolution of voids depend on dark matter's properties, how it clusters, how it interacts, how it affects the cosmic web. By studying voids, we gain constraints on what dark matter could be, ruling out some candidates and supporting others. The role of dark energy becomes clear through void studies as well. Without dark energy, cosmic expansion would decelerate, and voids would expand more slowly than observed. The accelerated growth of voids provides independent evidence for dark energy's existence and measurements of its strength. As our observations of voids improve, they become increasingly valuable tools for understanding dark energy's nature and evolution. There's also what voids teach us about initial conditions. The statistical properties of voids, how many exist of each size, how they're distributed in space, how they correlate with other structures, all reflect the initial density fluctuations from which structure formed. By comparing observed void statistics with predictions from different models of the early universe, cosmologists can test scenarios for what happened in the universe's first moments. Voids carry echoes of cosmic inflation, of quantum fluctuations, of the processes that set the universe in motion. Voids demonstrate the principle of gravitational instability, the idea that slight overdensities grow while underdensities empty out. This principle explains not just voids, but all of cosmic structure formation. It connects the quantum fluctuations of the early universe to the galaxies and clusters we see today, showing how a simple physical mechanism operating over sufficient time can produce the richness and complexity of the cosmic web. Understanding voids also requires understanding cosmology as a whole. You cannot fully explain voids without accounting for cosmic expansion, dark matter, dark energy, structure formation, and galaxy evolution. Voids are not isolated phenomena, but integral parts of cosmic structure, connected to everything else. Studying them means studying the universe itself in all its interconnected complexity. There's something elegant about how voids emerge naturally from our current cosmological framework. We didn't need to invoke special mechanisms or exotic physics to explain them. They arise inevitably from well-understood processes acting on initial conditions that themselves emerge from well-motivated theories of the early universe. This coherence, the way different pieces of our cosmic picture fit together to explain observations, gives confidence that we're understanding at least the broad outlines correctly. Of course, confidence should not become complacency. Anomalies and puzzles remain. Some void properties don't match predictions perfectly. The Hubble tension might involve void effects. The nature of dark matter and dark energy remains mysterious despite decades of research. Voids might yet reveal surprises that challenge our current understanding. Science progresses through cycles of confidence and doubt, each new observation both confirming existing ideas and hinting at gaps in our knowledge. Work in laboratories on Earth explain the same principles that work in laboratories on Earth explain the largest structures in existence. This universality is not guaranteed by logic, but appears to be a feature of reality, one that makes science possible and gives meaning to our efforts to understand the cosmos. And this understanding, built from observation, simulations, and theory, connects to something deeper about the human relationship with the universe, our attempts to map and comprehend our cosmic context. As we continue this slow drift through the story of voids, we'll explore the more contemplative dimensions of what it means to inhabit a universe with such structures, such scales, such profound expressions of emptiness and form. There's something psychologically compelling about the concept of cosmic voids, something that resonates beyond the scientific facts. We live on a small planet, orbiting an ordinary star in a galaxy that sits on the edge of an enormous bubble of near emptiness. This knowledge doesn't change our daily lives, doesn't affect the sunrise or the weather or the routines that structure our days, but it does provide a cosmic context for existence that earlier generations lacked. Human beings have always tried to locate themselves in the universe. Ancient cosmologies placed Earth at the centre, with the heavens arranged in nested spheres around us. The Copernican revolution displaced us from that centre, first to an orbit around the Sun, then to an unremarkable position in the Milky Way, then to a typical galaxy among billions. Now we know that even our galactic neighbourhood has a structure, and our position in that structure is somewhat peripheral, adjacent to vast emptiness. This knowledge could be interpreted as diminishing our significance. We're not at the centre of anything, not privileged in any cosmic sense, located on the edge of emptiness in a universe full of similar emptiness. The cosmos is indifferent to us, proceeding according to impersonal physical laws that operated long before life emerged and will continue long after life ends. From one perspective, this is humbling to the point of nihilism. But there's another perspective available, one that finds meaning not in centrality, but in comprehension. We're ordinary, yes, located in an unremarkable place at an unremarkable time. Yet we, arrangements of atoms that were forged in ancient stars, have managed to map our cosmic context, to understand voids and filaments and the web of structure extending across billions of light years. We've deciphered our cosmic address precisely because we're not special. Because the universe operates according to consistent laws that we can discover and understand. The same physical processes that created the local void created voids throughout the universe. The same quantum fluctuations that set those processes in motion governed the entire cosmos. When we study voids, we're studying universal phenomena, learning truths that apply everywhere, always. Our particular location gives us a specific view of these phenomena, but the phenomena themselves transcend our location. Understanding them connects us to the universe as a whole. There's also a kind of companionship in knowing we're not alone in our adjacency to emptiness. Billions of galaxies exist in similar situations, perched on the edges of voids or scattered through underdense regions. If life and consciousness have emerged elsewhere in the universe, as seems likely given its vastness, then perhaps other observers are also contemplating their proximity to cosmic voids, wondering what it means, reaching conclusions similar or different to ours. The physical isolation of void-adjacent locations might seem to emphasize cosmic loneliness, but it also highlights a different kind of connection. We're all made of the same elements, governed by the same physics, shaped by the same cosmic history. Distance separates us spatially, but commonality connects us conceptually. Every observer, wherever located, sees the same speed of light, the same gravitational constant, the same fundamental forces at work. The universe, for all its scale, maintains a kind of unity, and perhaps there's something fitting about humanity's position on the edge of a void. We're a species characterized by exploration, by pushing boundaries, by venturing into unknown territories. Living on the shore of cosmic emptiness metaphorically reflects our nature as wanderers and wanderers, always looking beyond what we know toward what we might discover. The void before us is not a wall but a frontier, an invitation to continue asking questions. This more contemplative view of our cosmic location doesn't require us to abandon the scientific understanding we've built. Science tells us what voids are, how they formed, what properties they have. Philosophy and personal reflection help us integrate that knowledge into our self-understanding, finding ways to live meaningfully in a cosmos that didn't design itself around our needs or preferences. Both perspectives are valid and necessary. As we continue exploring the implications of cosmic voids, this interplay between scientific understanding and philosophical reflection will deepen, revealing not just what voids are, but what it means to know about them. To exist in a universe that contains them, to be the kind of being capable of mapping emptiness across billions of light years. Throughout history, humans have made maps. We've charted coastlines and mountain ranges, rivers and roads, territories and boundaries. Maps give us control, help us navigate, transform unknown spaces into known ones. The impulse to map is deeply human, an expression of our need to understand and order our environment. And now we map the cosmos itself, creating atlases of galaxies, voids, and the vast structures that organize them. Cosmic mapping is different from terrestrial mapping in crucial ways. We cannot visit the places we map, cannot walk their boundaries or measure them directly. Everything we know comes from light, from photons that have travelled for millions or billions of years before reaching our telescopes. We reconstruct three-dimensional structures from two-dimensional images, infer distances from subtle spectral shifts, build models to fill gaps in our observations. Cosmic maps are acts of inference as much as measurement. Yet these maps are remarkably powerful. They've revealed the cosmic web, shown us where galaxies cluster and where voids stretch. They've traced the evolution of structure over billions of years, connecting the distant past to the present. They've tested theories, constrained cosmological parameters, and guided the search for new phenomena. Maps of the cosmos are both records of what we've learned and tools for learning more. The progression of cosmic surveys tells a story of expanding knowledge. Early catalogues counted thousands of galaxies. Later surveys measured millions, then tens of millions. Each new survey went deeper, covered more sky, and measured more properties per galaxy. The maps became richer and more detailed, revealing structures that earlier surveys missed and refining measurements of known structures. This process continues, with each generation of surveys pushing boundaries further. Modern surveys create maps in multiple dimensions. They record not just positions, but distances, colours, shapes, spectra, and time variations. They track how galaxies move, how they evolve, how they cluster. These multi-dimensional maps allow astronomers to test theories in ways that simple catalogues cannot, correlating different properties to understand physical processes. A galaxy's position in a void, its colour, its star formation rate, and its motion all connect to tell a story of how it came to be and what it will become. There's something almost miraculous about our ability to create these maps at all. The universe doesn't label its structures. It doesn't highlight voids or draw boundaries around clusters. We had to invent techniques to measure distances across cosmic scales, to determine which galaxies are physically associated and which merely appear close due to projection effects. We had to build instruments sensitive enough to detect light from objects billions of light years away, and computers powerful enough to process the resulting data. The maps we create are imperfect, of course. They have observational limits, regions they cannot probe, systematic errors that bias measurements in subtle ways. We cannot map the entire universe, only the portion visible from Earth, the contents of our cosmic horizon. Beyond that horizon, we can only speculate about what exists. Our maps are necessarily incomplete, representing a tiny fraction of all that is. But within their limits, cosmic maps are genuine representations of reality. The voids they show are real. The filaments connecting galaxy clusters actually exist. The large-scale structure is not an artifact of measurement, but a feature of the universe itself. When we look at these maps, we're seeing the cosmos as it truly is, albeit filtered through the limitations of our instruments and the biases of our cosmic location. Future surveys will improve these maps dramatically. New telescopes will probe deeper into space and further back in time. New techniques will measure properties we currently cannot access. The maps will become more complete, more accurate, and more detailed. Each improvement brings us closer to a comprehensive understanding of cosmic structure and evolution. And yet, there will always be limits. We can never map beyond the cosmic horizon. We can never observe with infinite precision. We can never remove all uncertainty from our measurements. The universe is vast and our view is necessarily constrained. Learning to accept these limits while pushing them as far as possible is part of what it means to do cosmology, to practice science on the grandest scales. This acceptance of limits while pursuing knowledge connects to a broader theme about human inquiry. We can understand much, but not everything. We can map large portions of the universe, but not all of it. We can answer many questions, but must acknowledge others remain unanswerable. This humility, combined with confidence in what we can achieve, characterizes mature science and mature philosophy. Science is often portrayed as purely objective, a method for discovering facts independent of human perspectives or narratives. But in practice, science involves storytelling as much as measurement. We construct narratives to make sense of observations, to connect disparate facts into coherent pictures, to communicate discoveries to others. The story of cosmic voids is one such narrative, built from data but shaped by how we choose to frame and present that data. Consider how we describe structure formation. We talk about gravity, quote zero, quote the cosmic web, about matter, quote one, quote from voids into filaments, about galaxies, quote two, quote different environments. These are metaphors, ways of making abstract physical processes comprehensible by connecting them to familiar experiences. Gravity doesn't literally sculpt, it attracts. Matter doesn't flow like water. Individual particles follow gravitational trajectories. Galaxies don't inhabit spaces the way organisms inhabit ecosystems. They simply exist in locations determined by initial conditions and subsequent dynamics. Yet these metaphors are useful, even necessary. They help us think about complex systems, make predictions, and communicate with others. A purely mathematical description of structure formation would be accurate but incomprehensible to all but specialists. Narrative descriptions make cosmology accessible, allowing broader audiences to engage with discoveries about the universe. The stories we tell about voids help people understand what voids are and why they matter, but narratives can also mislead. When we speak of voids as empty or bubbles, we create mental images that might not perfectly match reality. Voids aren't completely empty, and they're not bubbles with well-defined surfaces. Their statistical density decreases, regions where galaxies are less common than average. The boundaries are gradual, not sharp. The interiors contain matter, just less of it. Simplified narratives smooth over these complexities, which is both helpful and potentially distorting. There's also the narrative of cosmic evolution, the story of how the universe progressed from a nearly uniform state to the richly structured cosmos we observe. This narrative has a beginning, the Big Bang, a middle period of structure formation, and a future of increasing void domination. It's a story with arc and progression, cause and effect, before and after. We find such narratives satisfying because they match how we experience time and change in our own lives. Yet the universe doesn't experience itself as a narrative. It simply exists and evolves according to physical laws. The story structure we impose is human, a way of organizing information that might not reflect anything fundamental about reality. Other intelligent species might organize the same facts differently, telling different stories while describing the same cosmos. The narrative is a tool, not the truth itself. This doesn't invalidate scientific narratives. They're built on solid observational and theoretical foundations. They make predictions that can be tested. They explain phenomena in ways that pure data cannot. But recognizing their nature as narratives, as human constructions built from facts, helps maintain appropriate epistemological humility. We're not discovering the universe's own story, because the universe doesn't have a story. We're creating stories that help us understand the universe, which is a different thing. The story of cosmic voids, as we've told it here, emphasizes certain aspects while neglecting others. We've focused on formation and evolution, on structure and statistics, on cosmological implications. We could instead have told a story emphasizing the rare galaxies within voids, their individual histories and characteristics. or a story about the technical challenges of detecting and measuring voids, or a story about the scientists who discovered voids and mapped the cosmic web. Each story would be true but incomplete, highlighting different facets of a multifaceted reality. Perhaps the most honest approach is to tell multiple stories, acknowledging that each captures something real, but none captures everything. The scientific narrative of gravitational structure formation coexists with philosophical reflections on cosmic emptiness and human reactions to discovering our location in the universe. These narratives don't contradict each other but complement each other, each adding dimensions that the others lack. What matters is that the stories remain grounded in evidence, that they don't drift into pure speculation or wishful thinking. The universe is as it is, independent of our stories about it. Our narratives are valuable insofar as they help us understand reality, predict observations, and communicate with each other. When they fail in these functions, when they mislead or confuse, they need to be revised or replaced, and revision is ongoing. As observations improve and theories develop, the stories we tell about voids will change. Details will be added, errors corrected, emphasis shifted. The narrative is not fixed, but evolving, adapting to new knowledge just as the voids themselves evolve under the influence of cosmic dynamics. This adaptive quality of scientific 90 minutes, you've been here for 90 minutes, quietly, patiently, choosing this over everything else the world was offering you tonight. Do you know how rare that is? Most people cannot sit with something slow and meaningful for more than a few minutes before reaching for something louder. But not you. Not tonight. This channel exists for exactly this kind of person, and a like and subscribe is how we find more of them. It is how we find each other. Thank you for still being here. Now let's continue. This adaptive quality of scientific storytelling is a strength, not a weakness, evidence that the enterprise is functioning as it should. One of physics' deepest principles is the second law of thermodynamics, which states that entropy, roughly the degree of disorder in a system, always increases over time. This principle governs everything from cooling coffee to the eventual heat death of the universe, and it connects, in subtle ways, to the evolution of cosmic voids and the large-scale structure they inhabit. In the early universe, matter was distributed almost uniformly, with only tiny fluctuations in density. From one perspective, this uniformity represents high entropy, since the microstates, the possible arrangements of particles, were nearly equivalent. But from another perspective, the uniformity represents low gravitational entropy, since gravity prefers clumped matter to smooth matter. As the universe evolved, matter clumped into increasingly concentrated structures, creating the cosmic web we observe today. This clumping might seem to decrease entropy, violating the second law. After all, we're going from a smooth distribution to a structured one, from uniformity to complexity. But the second law applies to closed systems, and the universe's expansion provides an escape hatch. As the universe expands, the horizon grows, encompassing more volume. This growth provides additional phase space, effectively allowing entropy to increase even as structure forms. The entropy increase happens primarily through the growth of black holes and the conversion of gravitational energy into radiation. Voids fit into this picture as regions where gravitational entropy has decreased locally, but where overall entropy continues to increase globally. As voids empty and filaments densify, the contrast between underdense and overdense regions grows. This growing contrast represents increasing gravitational organization, a decrease in gravitational entropy in some sense. But simultaneously, stars form in the filaments, converting hydrogen into heavier elements and radiating energy into space. This radiation increases entropy, more than compensating for the decrease associated with structure formation. Over very long time scales, the universe will reach maximum entropy. All stars will burn out, all black holes will evaporate through Hawking radiation, and all matter will decay if proton decay occurs. The cosmic web, including its voids, will dissolve into a uniform sea of radiation and exotic particles, all at nearly the same temperature. This final state represents maximum entropy, the ultimate victory of the second law. The voids will no longer be distinguishable from filaments, and structure will be erased, but we're nowhere near that end state yet. The current epoch is one of rich structure, of ongoing star formation, of voids growing larger while filaments grow denser. Time's arrow points clearly from past to future, from the Big Bang toward the heat death. But we exist in an intermediate phase where interesting things still happen. Voids are part of that interesting middle period, features that exist because the universe hasn't yet reached equilibrium. There's something poignant about this trajectory. The cosmic web is temporary. The voids that seem so permanent on human timescales are merely transient features in the universe's longer story. They will grow and persist for trillions of years, but eventually even they will fade as the universe approaches its final state. Nothing lasts forever, not even the largest structures in existence. Yet this impermanence doesn't diminish the significance of what exists now. The cosmic web, with its filaments and voids, is the universe's current arrangement, the product of 13.8 billion years of evolution. It's the context in which galaxies form, stars ignite, planets orbit, and life emerges. Temporary or not, it's what we have, and it's worth understanding. The arrow of time also affects our ability to understand cosmic history. We can only observe the past through light that has travelled to us from distant regions. We see distant galaxies as they were billions of years ago, when light left them. But we cannot see the future. We can predict how voids will evolve, based on our understanding of dark energy and cosmic dynamics, but those predictions could be wrong. The future remains open, uncertain in ways the past is not. This asymmetry between past and future is fundamental to time itself. Entropy increases in one direction, not both. Causes precede effects. Memory records the past, not the future. The universe has direction, a flow from what was to what will be. Voids participate in this flow, growing from smaller proto-voids in the past toward larger, emptier voids in the future. Their evolution traces time's arrow across cosmic scales. Understanding entropy and time's arrow provides context for all the other things we've discussed about voids. Their formation, evolution, and ultimate fate are all governed by thermodynamics and the asymmetry of time. The second law ensures that voids will continue growing, that structure will eventually fade, that the universe proceeds irreversibly from Big Bang to heat death. This might seem depressing, but it's also liberating. We exist in a time when structure persists, when the universe is interesting. That won't last forever, but it's enough for now. For all we've learned about voids and cosmic structure, there remain fundamental limits to what we can know. Some of these limits are practical, matters of technology or resources that might be overcome with time and effort. But others are fundamental, built into the structure of the universe itself in ways that no amount of cleverness can circumvent. Recognizing both types of limits is part of mature cosmological thinking. The most obvious practical limit involves observational reach. We can only see so far into space before galaxies become too faint to detect. We can only observe the universe for a limited time before our own lifespans end. We can only build instruments so large and sensitive given available resources. These limits mean our maps remain incomplete, our catalogues partial, our understanding based on samples rather than complete censuses. Better technology will push these limits further, but they'll always exist in some form. Then there's the cosmic horizon, a more fundamental limit. Light from sufficiently distant regions hasn't had time to reach us yet, and as the universe accelerates, some regions are receding so fast that their light will never reach us. We cannot observe beyond this horizon, cannot map structures in those regions, cannot know what exists there. Our cosmic maps necessarily cover only a fraction of the total universe, the portion within our observable bubble. If the universe extends beyond our horizon, and most cosmologists believe it does, then vast regions exist that we can never observe. Those regions might contain voids, filaments, and clusters much like our local structures, or they might be different in ways we cannot determine. The universe beyond our horizon is forever unknowable through direct observation, accessible only through theoretical extrapolation. There are also quantum limits to measurement precision. The Heisenberg uncertainty principle sets bounds on how precisely we can measure certain pairs of properties simultaneously. While this usually matters only at microscopic scales, it has implications for our ability to reconstruct initial conditions perfectly or predict future states with arbitrary accuracy. The universe retains an inherent fuzziness at its base, a fundamental uncertainty that no measurement can eliminate. Theoretical limits arise as well. Some questions might be unanswerable not because we lack data, but because they're not well posed. Questions like, what caused the Big Bang, or what existed before the universe, might not have answers, because causation and temporal precedence are concepts that break down at cosmic origins. We're trying to apply familiar notions to situations where they don't apply, asking questions that language allows but physics does not. The nature of dark matter and dark energy represents a different kind of limit. We know these things exist through their gravitational effects, but we don't know what they are. Decades of searches for dark matter particles have yielded no definite detections. Dark energy remains even more mysterious, possibly the cosmological constant, possibly something more complex, but certainly something we don't understand. These are not merely technical problems awaiting solutions, but possibly deep mysteries about the nature of matter, energy, and space-time itself. There's also the possibility of unknown unknowns, phenomena or principles we haven't even conceived of yet. The history of science includes many examples of discoveries that revolutionized understanding in unexpected ways. Atoms, radioactivity, quantum mechanics, cosmic expansion, all of these were unknown or unexpected before their discovery. Perhaps there are similar revolutions waiting in our future, new phenomena that will reshape our understanding of voids and cosmic structure in ways we cannot currently anticipate. Acknowledging these limits is not defeatism. It's honesty about the nature of human knowledge and cosmic reality. We know much, but not everything. We can answer many questions, but not all. Some ignorance is temporary, awaiting better observations or cleverer theories. Some might be permanent, reflecting fundamental limits to what any observer can determine from within the universe. But within these limits, we can still accomplish remarkable things. We've mapped our cosmic neighbourhood. We understand structure formation. We've identified our location in the web and measured the properties of nearby voids. We've tested theories and constrained cosmological parameters. We've built a coherent picture of cosmic history from the Big Bang to the present. This is not complete knowledge, but it's genuine knowledge, hard-won through observation and reasoning. Perhaps the appropriate attitude is one of confidence combined with humility. Confidence that our methods work, that we're learning real truths about the cosmos, that our maps and models correspond to reality. Humility that our knowledge remains incomplete, that mysteries remain, that future discoveries might revise our current understanding. This balance between confidence and humility characterizes good science and good philosophy alike. And with this recognition of what we can and cannot know, we approach the final sections of our journey through cosmic voids. Moving from technical understanding toward more reflective contemplation of what it all means, not just scientifically but humanly, not just for cosmology but for our sense of ourselves in relation to the cosmos that contains us. There's a peculiar beauty in cosmic voids, a kind of aesthetic that emerges from their very emptiness. Where filaments and clusters might overwhelm with their density and complexity, voids offer simplicity and space. They're cosmic pauses, regions where the frantic activity of star formation and galaxy evolution gives way to quiet and stillness. In a universe characterized by ceaseless motion and transformation, Voids provide intervals of relative peace. This appreciation of emptiness has parallels in human art and philosophy. Japanese aesthetics, for instance, embrace mei, the concept of negative space, the emptiness that gives form to fullness, in painting, sculpture, and garden design. What's absent matters as much as what's present. The empty space allows the eye to rest, provides context for the elements that exist, creates balance and harmony. Cosmic voids function similarly in the architecture of the universe, providing the empty canvas against which galaxies and clusters become visible. There's also a meditative quality to contemplating vast emptiness. Human minds often seek stimulation, novelty, complexity. But there's a different kind of value in simplicity and spaciousness. Voids invite us to slow down, to appreciate what's not there rather than cataloguing what is. In an age of information overload and constant stimulation, the cosmic void offers a counterpoint, a reminder that absence and presence are both important, that sometimes less is more. The scale of voids contributes to their impact. 100 million light-years of near emptiness is difficult to visualize, impossible to experience directly. But the attempt to comprehend such scales stretches the imagination in valuable ways. We're forced to think beyond human scales of time and space, to grapple with magnitudes that dwarf our ordinary experience. This cognitive stretching is itself a kind of growth, an expansion of perspective that mirrors the expansion of space itself. Photographs of cosmic structure, while not literally showing voids since voids are defined by absence, do convey their presence through pattern and distribution. Maps of the cosmic web show how galaxies trace out filaments around darker regions where fewer galaxies exist. These darker regions are the voids, visible not through their own light, but through their influence on surrounding structure. They're defined negatively yet remain unmistakably present. Artists have sometimes engaged with cosmic themes, trying to capture the sublime scale and beauty of the universe. Representing voids presents unique challenges. How do you paint emptiness? How do you sculpt absence? Some artists use minimal marks on large canvases, suggesting vast spaces through economy of means. Others create installations that surround viewers with darkness, evoking the isolation of void-adjacent locations. These artistic interpretations don't claim scientific accuracy, but rather explore the emotional and aesthetic dimensions of cosmic emptiness. There's also beauty in the physics itself, in the elegant way gravity shapes structure, in the mathematical descriptions of void properties, in the correspondence between simple initial fluctuations and complex final structures. Physics reveals patterns and symmetries, relationships and principles that have their own aesthetic appeal. The equations describing void evolution are not just functional, but beautiful in their simplicity and power. This appreciation of scientific beauty is not universally shared or easily explained. For those attuned to it, there's a deep satisfaction in seeing how phenomena fit together, how diverse observations are explained by unified theories, how mathematics and reality correspond. The beauty is abstract, intellectual, but no less real for being so. It's the beauty of coherence and understanding of mysteries yielded to patient inquiry. Cosmic voids, then, are beautiful in multiple ways, as physical structures with interesting properties, as examples of natural pattern and organization, as invitations to contemplation, as challenges to representation, and as subjects of scientific understanding. Different people will find different aspects appealing, but collectively these perspectives reveal that even emptiness, even absence, can be rich with meaning and significance. Perhaps what's most beautiful is the fact that we can appreciate voids at all, that we're capable of measuring regions we can never visit, understanding processes that operate on timescales billions of times longer than human lives, finding meaning and value in knowledge of things that don't directly affect our daily existence. Our capacity for cosmic wonder is itself wondrous. A remarkable feature of conscious minds in a vast universe, Living on the edge of a void emphasizes a particular kind of cosmic loneliness. The nearest large concentrations of galaxies are millions of light years away. Most of the volume around us is empty or nearly so. If we could somehow travel at the speed of light, it would take tens of millions of years to traverse the void and reach the denser regions beyond. We're isolated, perched on the shore of an ocean of darkness that stretches further than we can easily comprehend. This isolation is physical, but also in a sense communicative. If other civilizations exist in our cosmic neighbourhood, they face the same vast distances. Signals travelling at the speed of light would take millions of years to cross between galaxies in void-adjacent regions. A conversation would require millions of years per exchange. Any contact would be asynchronous, messages in bottles cast into the cosmic ocean, with no guarantee of reception or response within any civilization's lifetime. Yet this very isolation creates a different kind of connection. Every galaxy near the local void shares our situation. Every potential civilization in those galaxies would face similar challenges, similar scales of loneliness and distance. There's a community, albeit one separated by unbridgeable gaps, of isolated observers all contemplating similar cosmic contexts. We're alone together, sharing a condition even if we cannot directly communicate. The history of human isolation and connection provides imperfect but useful analogies. Island cultures developed unique characteristics due to their isolation, yet shared common responses to island life. Antarctic researchers experience profound isolation, yet report feelings of connection to previous generations of researchers who endured similar conditions. Astronauts orbiting Earth are physically separate from humanity, yet feel deeply connected to the planet below. Isolation and connection are not opposites, but coexisting dimensions of experience. Cosmic loneliness might also be provisional. Current physics places the speed of light as an absolute limit to communication and travel, but our understanding of physics is incomplete. Perhaps future discoveries will reveal ways to bypass this limit, enabling communication or even travel across cosmic distances in reasonable times. This seems unlikely based on current knowledge. But the history of physics includes many revised limits and abandoned certainties. What seems impossible might merely be unknown. Even without faster-than-light communication, there's connection through shared reality. The same physical laws govern all galaxies. The same chemical elements exist everywhere. The same processes of star formation, planet creation, and potentially life operate throughout the cosmos. An alien scientist studying voids in their galaxy would discover the same principles we've discovered, reach similar conclusions, build compatible models. Our knowledge connects us across gulfs that no signal can cross. There's also connection through time. Photons from distant galaxies carry information about their sources, creating a kind of communication even if it's one way and delayed. When we observe a galaxy 100 million light years away, we're seeing it as it was 100 million years ago. We're receiving a message from its past, learning about its properties and history. In principle, observers in that galaxy could observe ours and learn about our past. Time delayed, one-directional but genuine exchange of information across cosmic distances. The Voyager spacecraft, launched in the 1970s and now beyond the solar system, carry golden records with information about humanity and Earth. These records will outlast human civilization, potentially surviving for billions of years in interstellar space. They're messages to no specific recipient, statements that we existed and wanted to be known. Perhaps other civilizations have launched similar messages, artifacts drifting through the void waiting to be found. Loneliness seeks to overcome itself through such gestures, even when success is uncertain. But perhaps the deepest connection is internal, within our own minds and communities. We're conscious beings capable of understanding our cosmic context, of feeling both loneliness and wonder at our situation. We can share these feelings with others of our species, creating human connections that acknowledge and respond to cosmic isolation. art, philosophy, science, conversation, all these are ways we reach across the smaller distances that separate human minds, building understanding and community in response to the larger cosmic loneliness. The paradox is that cosmic isolation might actually enhance human connection. Knowing we're in this together, on a small planet near a cosmic void in a vast universe, provides perspective that can strengthen bonds between us. Our differences seem smaller when set against cosmic scales. Our shared humanity becomes more precious when we recognise how rare and fragile it might be in cosmic context. Isolation from the cosmos might bring us closer to each other, and maybe that's enough. Maybe connection across cosmic distances isn't necessary or even desirable. Maybe the appropriate response to cosmic scale is not to try to fill all the emptiness, but to appreciate the oases of matter and life where they exist, to value the connections possible at smaller scales, to find meaning in local community rather than cosmic communication. The voids might be reminding us that not everything needs to be connected, that distance and separation are also parts of existence, that loneliness is a condition to be acknowledged and lived with rather than a problem requiring solution. Cosmic distance provides perspective in the most literal sense, a viewing position from which to observe and understand. The distance between us and distant galaxies allows us to see them as they were at different cosmic epochs, effectively giving us a time machine pointed at the past. The distance across voids lets us measure cosmic expansion and test cosmological models. Distance is not just empty space between objects, but a resource we use to learn about the universe. This perspective extends beyond the purely scientific. Knowing about cosmic scales changes how we think about terrestrial concerns. Problems that seem insurmountable on human scales become almost invisible against cosmic backgrounds. Political disputes, economic anxieties, personal troubles, all these retain their immediate importance but acquire a different quality when we remember they're occurring on a small planet near a cosmic void in an expanding universe. This isn't to dismiss human concerns, but to frame them within a larger context. The overview effect, reported by astronauts seeing Earth from space, describes a cognitive shift triggered by viewing our planet as a whole. From orbit, national boundaries are invisible. Human conflicts seem petty. The fragility and unity of Earth become apparent. Cosmic perspective offers something similar but more extreme. Seeing our galaxy as one among billions, our local cosmic structure as ordinary, our entire observable universe as potentially a small fraction of total reality. These recognitions shift perspective in profound ways. Some might worry that cosmic perspective leads to nihilism, to concluding that nothing matters because everything is so small and temporary against cosmic scales. But this concern conflates scale with significance. Small things can matter deeply. Temporary things can have value. A human life, though brief and spatially tiny, contains experiences, relationships and consciousness that are intrinsically meaningful, regardless of cosmic context. Perspective should enhance appreciation for what we have, not diminish it. There's also a cognitive freedom in cosmic perspective. When you realise that the universe is vast, ancient and largely indifferent to human concerns, you're freed from certain illusions about cosmic purpose or design. The universe wasn't made for us. We're not the centre or the goal. But this means we're free to create our own meanings and purposes, to decide for ourselves what matters and why. Cosmic perspective can be liberating rather than depressing if we let it. The scale of void specifically teaches humility. No matter how much empty space seems to dominate human experience, whether geographical distance, social separation or emotional isolation, it's nothing compared to cosmic voids. 100 million light-years of near emptiness makes any human experience of emptiness seem almost cozy by comparison. This isn't to invalidate human experience, but to provide scale, to remind us that what we endure is small, manageable, survivable in cosmic terms. Perspective also teaches patience. Cosmic timescales stretch billions of years. Voids took most of cosmic history to reach their current size, and will take trillions more to reach their ultimate state. Nothing in the cosmos happens quickly. Stars take millions of years to form. Galaxies merge over hundreds of millions of years. Structure evolves on timescales that dwarf civilizations. This patience, this acceptance of gradual change, might offer lessons for human life, reminding us that not everything happens immediately, that some processes require time and cannot be rushed. There's something both humbling and empowering about cosmic perspective. Humbling because we're forced to recognize our smallness and brevity. Empowering because we, small and brief as we are, have managed to understand so much about the vast and ancient cosmos. Our minds can encompass scales far beyond our bodies. Our mathematics describes phenomena we can never directly experience. Our theories explain processes that operate across billions of light years and billions of years. Perspective reveals both our limits and our capacities. Perhaps the greatest gift of cosmic perspective is simply the invitation to wonder, to step outside ordinary concerns and contemplate the extraordinary nature of existence itself. That there is a universe at all, that it contains structure and variety, that conscious minds have emerged capable of studying it. These are all remarkable facts worth pondering. Voids, in their very emptiness, highlight the remarkable nature of what does exist, the galaxies and stars and planets that punctuate the darkness, and wonder. Life that includes wonder is richer than life that includes wonder is richer than one without, regardless of other circumstances. Cosmic voids, improbable as it might seem, can contribute to that richness by giving us something vast and strange to contemplate. Something that stretches imagination and invites deeper thinking. Despite everything we've explored about voids and cosmic structure, mysteries remain. We don't know what dark matter is, what dark energy is, how the universe began, whether it will end, why physical constants have their particular values, whether other universes exist. What happened before the Big Bang, if that question even makes sense? These are not gaps that will necessarily close with more research. Some might be permanently beyond human understanding. Learning to live with mystery is part of intellectual maturity. Young students often expect that science has answers to every question or soon will. Mature scientists know better. They recognise that answering one question often raises three more, that deeper understanding reveals deeper mysteries. That knowledge is an island in an ocean of ignorance, and every expansion of the island increases the coastline when known meets unknown. The mysteries surrounding voids are relatively minor compared to the fundamental mysteries of physics and existence. We understand voids reasonably well within our current cosmological framework. They form through gravitational structure formation, grow through cosmic expansion and dark energy, and contain sparse populations of galaxies and dark matter. These are not wild speculations, but well-supported conclusions. The mysteries are more about details than fundamentals, but those details matter. Why do some voids contain more galaxies than expected? Are there dark galaxies we haven't detected? How precisely does dark energy affect void evolution? What happens in the far future as voids dominate cosmic volume? These questions have answers we haven't found, and pursuing them will likely reveal new phenomena and principles. Mystery drives investigation, and investigation sometimes resolves mystery while always uncovering new questions. There's a difference between mystery and mysticism, between acknowledging what we don't know and claiming special knowledge through non-rational means. Mystery, in the sense meant here, is simply the honest recognition of limits to current understanding. Limits that might be overcome through future research or might prove fundamental. Mysticism claims to transcend those limits through revelation, intuition, or faith, rather than observation and reasoning. The former is intellectually honest. The latter is epistemologically suspect. Cosmic voids don't require mysticism to be meaningful or worthy of contemplation. Their scientific description is sufficient to provoke wonder and raise philosophical questions. We don't need to attribute consciousness to voids or see them as portals to other dimensions or invest them with spiritual significance to find them interesting. The facts alone, the 100 million light years of near emptiness, the gravitational history that created them, the slow evolution under dark energy's influence, these are remarkable enough without embellishment. Some mysteries might be welcome rather than frustrating. If we knew everything about the cosmos, if no questions remained, would that be satisfying or disappointing? Part of what makes exploration worthwhile is not knowing what you'll find. Part of what makes science exciting is the possibility of surprise. Mystery preserves that possibility, keeps the universe interesting, maintains the excitement of discovery. There's also the recognition that human understanding might be inherently limited. We evolved to navigate terrestrial environments, to understand medium-sized objects moving at moderate speeds. Our intuitions fail at quantum scales and cosmic scales. Perhaps there are aspects of reality that human minds, even aided by mathematics and technology, cannot fully grasp. This possibility is worth entertaining without accepting it prematurely as an excuse for giving up investigation. But if some mysteries do prove permanent, if some questions remain forever unanswered, that's acceptable. We can still achieve partial understanding, still make progress, still learn immense amounts, even while acknowledging that complete knowledge eludes us. Science doesn't require omniscience to be valuable. Partial, uncertain, provisional knowledge is still knowledge, still useful, still worth pursuing. The acceptance of mystery connects to the acceptance of our cosmic situation more generally. We're finite beings in an infinite or effectively infinite universe. We live briefly on cosmic timescales. We observe from one location, one moment in cosmic history. These constraints are facts about our existence, not problems requiring solutions. Accepting them allows us to focus on what we can achieve rather than lamenting what we cannot. And perhaps mystery serves another purpose, a more existential one. It reminds us that reality exceeds our comprehension, that we're not the measure of all things, that the universe doesn't owe us complete understanding. This reminder can be grounding, a useful corrective to human arrogance. We're part of the cosmos, not separate from or superior to it. Mystery acknowledges our participation in something larger than ourselves. Living with mystery, then, is not defeat but wisdom. It's recognizing limits while pushing against them, acknowledging ignorance while pursuing knowledge, accepting what cannot be known while investigating what can. This balanced attitude characterizes the best cosmology and the best philosophy, neither claiming too much nor demanding too little, neither arrogantly asserting omniscience nor nihilistically abandoning inquiry. As we approach the end of this long drift through cosmic voids and human responses to them, there's a peace to be found in recognizing the rhythms of the universe, the patterns that repeat at all scales, the cycles that connect the very small to the very large, the patterns of condensation and dispersal, gathering and emptying, light and darkness that characterize cosmic existence. Voids and filaments create a rhythm in space, a pattern of fullness and emptiness that organizes matter across the larger scales. This pattern is not random but structured, not chaotic but organized by gravity's patient work over billions of years. There's order here, comprehensible order, mathematical order, the kind of order that human minds can grasp and find satisfying. The cosmos, for all its scale and complexity, operates according to principles we can understand. There's also rhythm in time, the cosmic evolution from uniformity to structure to eventual return to uniformity. The universe breathes, in a metaphorical sense, exhaling structure during its Middle Ages and eventually inhaling toward maximum entropy, though this inhalation will take trillions of years. We exist during the exhalation, when structure is rich and complex, when voids grow but haven't yet dominated, when stars shine and galaxies cluster, and life contemplates its cosmic context. This rhythmic view of the cosmos can be calming. Change happens, but within frameworks. Evolution occurs, but according to principles. The universe is neither static nor arbitrary, but dynamic and lawful. This predictability, this reliability of natural law, provides a kind of cosmic stability, even as individual structures come and go. The laws persist even when particular instances pass. Darkness and light alternate not just in day and night, but in cosmic structure. The voids are dark, not because they contain no light, though they contain little, but because they contain few sources of light. The filaments are bright with galaxies, each galaxy a concentration of stars, each star a fusion furnace producing light and heat. This alternation of dark and light creates the cosmic pattern, gives shape to structure, makes the universe visually comprehensible when we map it. There's a meditative quality to contemplating this pattern, this cosmic arrangement of presence and absence, light and dark, matter and void. Meditation often involves attention to patterns, breathing patterns, sensory patterns, thought patterns. Cosmic meditation might involve... Before I say goodnight, I need you to know something. When this video was posted, most people scrolled right past it. They saw the length, they saw the topic, and they kept scrolling. But you didn't. You stayed for 2.5 hours, you chose depth over speed, and wonder over noise, and I think that says something beautiful about the kind of person you are. If this channel has given you something tonight, a little more peace, a little more wonder, a little more understanding of the world you live in, then a like and subscribe is the kindest thing you can leave behind before you sleep. Not just for this channel, but for the next person out there tonight who needs exactly what you just found here. Now, rest. You have earned it. Cosmic meditation might involve attention to the largest patterns, the structures that organize the universe itself. Such attention can quiet the mind, shift perspective, create calm. The peace offered by cosmic contemplation is not escape from reality, but deeper engagement with it. Looking at stars, thinking about voids, recognizing our place in vast structures, these activities ground us in reality, remind us that we're part of something larger, connect us to the cosmos that created us. This connection can be reassuring, can provide perspective that makes daily troubles seem more manageable. There's something fundamentally peaceful about the fact that the universe simply is, that it exists and evolves according to its nature without requiring our understanding or approval. It doesn't need us to validate it. It was here long before we emerged and will persist long after we're gone. This independence can be freeing rather than threatening if we approach it with the right attitude. The universe doesn't need us, which means we're free to find our own purposes within it. The stars in filaments and clusters will continue fusing hydrogen regardless of human concerns. The voids will continue expanding whether we understand them or not. Cosmic evolution proceeds on its own timescale. Indifferent to our hopes and fears, this indifference is not cruel but simply neutral, a feature of reality that we can accept and even find peaceful. We don't have to carry the universe's weight. It carries itself. And so, as our journey through cosmic voids comes toward its close, we can rest in this understanding. We've explored the science, contemplated the implications, considered the philosophical dimensions. We've mapped our cosmic neighbourhood and recognised our location's character. We've acknowledged mysteries and celebrated partial understanding. We found meaning in structure and beauty in emptiness. The cosmic web, with its voids and filaments, its dark matter and dark energy, its billions of galaxies flowing through space, exists as it is. We exist within it, briefly but genuinely, conscious bits of the universe that have organised themselves into forms capable of studying the whole. This is remarkable enough to justify wonder, complex enough to reward investigation, vast enough to provide perspective, and peaceful enough to invite rest. Let the voids expand in the darkness. Let the galaxies flow along their filaments. Let the universe evolve according to its nature. And let us, small as we are, find peace in understanding our place within it all, neither central nor meaningless, neither permanent nor insignificant, simply here, now, aware, contemplating the cosmic architecture that is our context and our home. We've travelled together through 150 minutes, 2.5 hours of slow exploration through cosmic voids, human responses, scientific understanding, and philosophical reflection. Thank you for staying for the entire journey, for giving this much time to contemplating emptiness and structure on the larger scales. From the discovery that we live near the local void, to the recognition of the cosmic web stretching across billions of light years, from the physics of structure formation to the philosophical implications of cosmic scale, from the loneliness of void, adjacent locations to the peace available in cosmic perspective, we've covered substantial ground, or perhaps more accurately, substantial space and thought. The question we began with, what it means that we're trapped in a cosmic void, or more accurately adjacent to one, has found several answers. Scientifically, it means we occupy a particular location in the cosmic web with specific observational consequences. Philosophically, it might mean recognizing our isolation while finding connection in shared cosmic context. Emotionally, it can mean whatever we choose, from existential anxiety to contemplative calm. Perhaps the answer, as honestly as I can give it, is that living near a cosmic void is simply a fact about our existence. One fact among countless others, neither terrible nor wonderful in itself, but potentially meaningful, depending on how we engage with it. The void itself doesn't care about us, but we can care about the void, can study it, understand it, find it beautiful or interesting, use it to gain perspective or provoke wonder. The meaning is not in the void, but in our relationship to knowledge about it. If you enjoyed this slow drift through cosmic structure and human contemplation, a like and subscribe really helps others find these explorations. And if you have thoughts about voids, about cosmic perspective, about what you've heard tonight, the comments are always open. To those who've accompanied me on previous journeys through space and time, thank you for returning. To those discovering this for the first time, welcome to this community of cosmic contemplation. Wherever you are in the world right now, in whatever time zone, whatever weather, whatever circumstances surround your listening, I hope this exploration has provided some value. I hope your breathing has slowed since we began. I hope your thoughts have quieted somewhat. I hope your body feels heavy and comfortable, ready for rest. Look up at the stars if you can, on a clear night when you get the chance. Remember that between those points of light stretch vast distances, that most of space is void or nearly so, that the matter we see is concentrated along filaments surrounding enormous bubbles of emptiness. All those stars, all those galaxies, all that structure emerges from and exists within a cosmic architecture of light and darkness, presence and absence, fullness and void. We participate in this architecture, made of atoms forged in ancient stars, living on a planet near a void, observing a universe that created us through billions of years of evolution and structure formation. We're part of it all, brief and small but genuine and aware. The voids that surround us are not threatening but simply features of our cosmic home, aspects of reality worth understanding and even appreciating. Sleep well tonight, whether you drift off now or stay awake a while longer. Dream of cosmic voids if you like, of vast empty spaces crossed slowly by lonely galaxies, of filaments connecting clusters across unimaginable distances, of dark matter webs and dark energy's gentle push expanding space itself, or dream of smaller things closer to home. Either is fine. Rest in the knowledge that the universe persists in its patient evolution, whether we wake or sleep. Rest in the perspective that our concerns, significant as they are to us, occur within a vastly larger context. Rest in the peace that can come from understanding our place in cosmic structure, neither central nor meaningless, simply here, aware, part of the whole. Good night from the edge of the local void, from a small blue planet circling an ordinary star, from conscious arrangements of matter contemplating the nature of cosmic emptiness and fullness, darkness and light. Good night, and may your rest be deep and peaceful.